to martensite and retained austenite. Okay, retained austenite is not exactly the same as austenite. Austenite over here is at high temperature. Retained austenite and martensite are room temperature. Okay, so why we have retained austenite? Because the transformation is not 100%. Okay, the best you can get is 10% retained austenite. Sometimes can be more. Okay, can be more. So what do I mean by this? Okay, so we're going to look into our phase diagram. As I said, after my work with Uzbor, I appreciate material science. Okay, still very hardcore mechanical, but I begin to read more on material science textbook. Okay, any material science textbook would do. Okay, it's all about fundamentals. So if we look at the phase diagram, you have percentage of carbon, you have temperature, okay, degree C. Then you have your you're going to have your 723 line. Okay, then you will have different I'm going to stop at 0.77. So the steel composition is 0.123, so it's somewhere around here. As we know, this is your ferrite plus pearlite. Over here is your austenite. Then over here is your ferrite plus austenite. Okay. So in this process, what they do, right, or how a lot of companies process this material is they will heat up okay somewhere around here, right? They'll heat up somewhere around here. And after they heat up, now where is critical, okay, which I discovered. Okay, so depending on where this is, okay, so we have a certain temperature theta H. Okay, so theta H is the holding temperature. So after they hold, right, after holding, the material is at its holding temperature. Okay. The material is quenched, okay, to form martensite, like what I've written before, plus retained austenite. Okay, right? So I was desperate. Okay, after 3 months there, I tried everything. There was no conclusion at all. I even measured the hardness. Okay, I even tried to do some tensile tests. Sometimes I see significant difference. Sometimes I don't. But why this difference? Yeah, that's the thing. Okay, Then I realized, okay, let's apply. Okay, let's apply Lever's rule. Okay, Lever's rule to determine effect of temperature on microstructure. Okay, so I have to take up my textbook. Okay, how to use Lever's rule. Okay, and I believe some of you do know Lever's rule. Okay, so if not, I will go through Lever's rule with you guys. Okay. Any questions so far? Anyone?
Are you holding the temperature at 723? Is that what it is?
No, I mean it's not at 723 for this case. Okay.
Oh, 723 is the line that goes across. Okay, thanks.
Yeah, 723 is the line that goes across. It's the eutectic temperature. Okay. So I'm gonna expand. I'm gonna expand this part of the graph. Okay. Of the phase diagram. I'm gonna blow this up. Okay. So now we have percentage of carbon. And this is temperature. Okay. So this is the 723 line. Okay. So this is just a sketch. Right? No, this one should look like that. Okay. So I started calculating. Okay, if I range the temperature, this amount will happen. So I took it at 750. Okay, I took it at 750. Over here is 800 and 775. So I vary the temperature, 3 different variation. So we are aware at this side, okay, it's austenite. Right? At this side, we have ferrite. Okay. So whatever is in between, right, is your austenite plus ferrite. Okay. So when it touches this line represent, okay, 100% austenite, 0% ferrite. Okay. Whereas the other line, okay, this line over here, right, it represent 0% austenite and 100% ferrite. Okay. So if we pick a temperature of 800, for example, now we pick a temperature of 800, right? And then again, this is just a sketch. We project a line up. This line that we project is at 0.123% of carbon, right? Then from here, we use Lever's rule to calculate the percentage of austenite and ferrite. Okay, So over here, this over here, this is at 0.31. Okay. Yeah, so this number is important. Over here, the number is 0.03. Okay. So we are going to apply Lever's rule. Okay. So my advice is to work on austenite. We are so used to what? Okay, the left hand side is 0, right hand side is what? 100. Left hand side means left hand side is 0. So let's work with austenite first. Okay. So we calculate austenite. Okay, percentage of austenite. So the range below is 0.031 or 0.31 minus by 0.03. The carbon starts at 0.123 minus by 0.03. Okay. Then you multiply by 100.
Sorry, what's in the numerator?
0.123 minus by 0.03 divide by 0.31 minus by 0.03. Does that make sense?
Yeah, why those numbers? Why 123 minus 0.03?
Okay, okay. So what are those numbers? Okay. So if we look at this line over here, right? So this line, this is 0% of austenite. Over here is 100% austenite. Right? So it's a percentage that we want to know. And if you look at the carbon, this is 0.03 and this is 0.31. If we are at 0.123, right? Sorry, not here. If now, so this is also a linear scale, okay? There are linear relationship. So if it's 0.123, right? We want to find what is the percentage of austenite. So we want to find how many percent, what is this austenite value? Does that make sense to you? So it's like a linear interpolation. Okay, if I were to draw this in a graph form, in a mathematical form, so this is percentage of carbon. This is austenite, right? And this is a linear scale. All right, this is a linear scale. I wonder is this a good representation, but let's see. If this is a linear scale, right? So 0 is if it's 0% austenite. Wait, no. It has to cross through 0.
Sorry, I was just wondering, sorry, 0.03, that's the percent of carbon on that line or at the holding temperature?
At the holding temperature. Right? Remember, I draw this line up to here. You okay?
Yeah, thanks.
Okay. And then over here you have 0.03 or 0.31. And this is 0, this is 100. We want to find at 0.123 what is this value. Okay. So we apply Lever's rule. So mathematically, if you have percentage of carbon and austenite over there, okay, translated, you get the same thing. Okay. But it's linear, so you can apply this we call it Lever's rule.
Awesome,
So
thank you.
welcome. I thought you cannot see those numbers. So, okay. And then 0 by 0.31 minus 0.03. So it's 33.2.